is to talk about what we work on. Did I say our names? No.
Yes.
So I work on developing TKIT, and Callum is our primary outreach person. So Callum is going to give you an intro to what TKIT is, mostly in slides. He'll have some code examples that we can share with you later. And then, so that'll be approximately the first hour, and then approximately the second hour, I will go through some more advanced code examples live. I'll talk more about the code in a second. Actually, as a quick straw poll, just because we have a very little idea of what everyone's background is and how to pitch this. So could you put your hands up if you've programmed in Python before? Okay, that's very good. Could you put your hand up if you have written a quantum circuit in Python before? Yeah, no, that's good. So that's some people, okay. And then finally, if you've run a circuit on either a simulator or a real device. Similar, okay. All right. Obviously, there's a range of backgrounds here, and so we don't want to leave anyone behind. We will be starting simple and going harder, but just stop us to ask questions whenever, right? This isn't going to be linear. Just because it's slides doesn't mean you have to listen to Callum. Put your hands up, shout out. The whole 2 hours is going to be as interactive as we can make it. Okay, you will introduce the code stuff?
Yep.
So for the starting, you won't need to be coding along. We will talk more about joining along with it later on as we get into it. I will leave you with Cal.
Okay, thanks. Yeah, great to be here. Thanks to everyone that was involved in setting this up. As Sion mentioned, my name's Callum, and I'm here to talk about TKIT, our software package for quantum computing. So yeah, Sion's been through some of this already, but there'll be an intro session, which is now. There'll be an advanced session presented directly after. Then it'll be a joint session with Sion and Eliza, and there'll be a hackathon later in the event as well. So I've made a public repository, Qalypso 2022, and there are some exercises and instructions on how to install TKIT there. There's some warm-up challenges as well, which feel free to give those a try whenever you like. And yeah, I've made a Slack channel as well. I noticed some of you have already joined that. Yeah, the link is in WhatsApp. Okay, so yes, I'm going to give you an overview of some of the challenges of quantum computing, and then I'm going to cover a bit of how TKIT can help address those challenges. So first problem with quantum computing is noise. So you've probably heard this acronym, NISQ. This stands for Noisy Intermediate Scale Quantum. This means we have sort of intermediate scale devices of approximately 50 to 200 qubits at state of the art. These qubits are noisy, they have high error rates, and we cannot implement quantum error correction codes using those devices. This means every operation in our circuit is noisy, and therefore a large circuit size with lots of quantum gates means that noise accumulates and corrupts your results. What this means in practice is that many of the sort of textbook quantum algorithms are very difficult to realize on modern devices. So these classic algorithms like Shor's algorithm and Grover's algorithm are very challenging to work with. Secondly, there's the issue of device constraints. So quantum computers typically support a small universal gate set, and the algorithm you may want to run may be written in terms of other gates. So what's more, certain devices have a restriction that you may only be able to realize multi-qubit interactions between specific pairs of qubits. So your algorithm needs to be rooted to the connectivity constraints of the device. Yes, this is related to a problem called the qubit routing problem. Yeah, to satisfy the connectivity constraints, you need to add often these additional swap gates, which add additional gates to your circuit and therefore introduce more noise. Yeah. Like Seon said, if there's any questions, feel free to just ask. Okay. So just to give you a bit of an example of what I was talking about in the previous slide, I've included a layout of one of IBM's devices. This is IBM's Guadalupe device. It's a superconducting device. And here is a diagram showing how the qubits are laid out. So if I want to realize a 2-qubit gate between qubit 1 and qubit 7, I'll need to add one swap gate in order to validate that interaction. Okay. So I noticed you've covered Grover's algorithm already. So why can't we just set up our Grover's circuit and then just run it straight away on our device? Well, you notice that in this diagram, the Grover's algorithm is defined in terms of higher level operations. So you have this oracle here, followed by this Grover diffusion operator. And these operations can't be realized natively on the device. We need to compile the circuit down into a form that can actually be executed. So this circuit currently is not able to be run on the IBM device because it doesn't meet the device constraints on the gate set and the connectivity. So I've included another example of a circuit that is compiled down to the operations, the gates that the device supports. So you can see instead of these higher level box structures like this oracle and this diffusion operator, we instead have just single and 2-qubit gates here. So this circuit is valid, it meets our device constraints, and therefore we can run this on our IBM device. The third issue I'm going to talk about, which isn't a fundamental issue so much as an inconvenience, is this issue of code portability, for lack of a better term. So quantum computers have different architectures. You have superconducting devices, you have trapped ions, you have many other types of device, neutral atoms or photonics. And each of these device types have their own pros and cons. So a natural thing you might want to do is try out different devices to see how your algorithm performs. Problem is that accessing a particular device may require specific software to interface with this device. So you may end up having to rewrite large chunks of your code, and this is just an inconvenience. Okay. So now that I've covered some issues with quantum computing, I'm going to introduce TKIT. So what is TKIT? TKIT is a quantum computing toolkit and optimizing compiler. So what do I mean by this? So TKIT is designed to improve the performance of algorithms running on NISQ devices. And the way it does this primarily is by optimizing quantum circuits to reduce the resources required to perform these algorithms. TKIT is also retargetable in that it can interact with many different devices and simulators, as well as integrates with several popular quantum computing libraries, including Qiskit and Cirq and several others. And yes, this command here, you can just install TKIT through the Python bindings by just using the pip package manager, so pip install pyTKIT. Yeah, so TKIT itself is implemented in C++, but you access it through a Python API. Okay. So how does TKIT interact with all these different libraries and backends? Well, TKIT has several different extension modules, including Qiskit, pyTKIT Qiskit, and Cirq, and so on. And these extensions provide the ability to interact with these different libraries here, these different input formats, and target different devices and simulators. So you can see you have a Quantinuum backend here for accessing Quantinuum's ion trap devices and simulators. And there's also one for IBM-Q and Rigetti and several others. Yeah. So yeah, the installation command for this is just pip install pyTKIT and then whatever the extension name is. So yeah, these are just separate Python packages that enable this extra functionality. Okay, so let me wave my hands a bit and build some intuition around circuit optimization. So what are these graphs showing here? Well, I've performed a phase estimation experiment using an emulator from IBM Q for Jakarta. And on the left, I have the experimental results that come from my circuit before I've tried to optimize it to reduce the size of the circuit. And you can see I've the thing that's nice about phase estimation, at least in this case, is that the correct answer corresponds to this basis state here. So this measurement result. I've executed my circuit 1,000 times, I've performed 1,000 shots, then I've plotted the proportion of my shots that correspond to the correct answer. You can see in this unoptimized circuit that about 299, roughly 300 of my shots correspond to the desired outcome. This circuit has 232 gates and 124 two-qubit gates. I've then tried to optimize my circuit here using the techniques available in TKIT, and I've managed to increase my success probability. So 524 out of 1,000 shots are now landing in the desired basis state here. So I've improved my success probability from about 30% to about 52%. It's worth noting here this discrepancy in the number of CX or C0 gates. These are a sort of dominant source of error, so they're a natural metric to try and minimize when you're thinking about circuit optimization. Okay. Okay, so now I'm going to jump into some basic code with TKIT. So how do I build a basic circuit? Well, you've had a Qiskit session already, and you'll notice that the API for building circuits is, in many ways, quite similar to Qiskit here. So I import my circuit class. I can then create an instance of my circuit class with 2 qubits. I can then add a Hadamard gate just directly by appending this. I can add a controlled NOT gate with target control qubit 0 and target qubit 1. Then finally I can measure. And I can draw my circuit with this render circuit Jupyter function here. You'll notice that there's also these GUI icons here on the side of the diagram. And these are for toggling between different representations of your circuit. For instance, there's option to view your circuit as a ZX diagram, if you're familiar with that. I know you'll have heard from Bob on Monday about that. So let's consider a less trivial example of a circuit. So I was talking about phase estimation earlier. Let's look at a phase estimation circuit and see, use that as an example to illustrate some features of TKIT. So instead, I could define this phase estimation circuit from scratch with TKIT. It's not too hard, but I'm going to instead just load this in from a QASM file. So QASM is just a way to specify quantum programs at a low level. And it's a sort of standard way of representing quantum circuits. So I can just load this circuit in by using this circuit from QASM function here. And this, I can just create this circuit and visualize this as before. You'll see that I've got 12 gates in total, and 5 of these gates are these 2-qubit gates that act between 2 qubits. And I'm counting my gates here with this op-type enum here. So I'm just counting the number of CU1 gates as well as the number of swap gates here. These are controlled U1 operations. These are parameterized gates. I think they are very similar to CRZ gates, but they differ by a phase. Okay. Okay, so I'm just going to load in a slightly bigger version of my circuit here because I think certain things later in the presentation will become clearer. So from now on, I'll be working with this phase estimation circuit that has an extra qubit instead. So I now have 21 gates and 11 multi-qubit gates. Okay, so now that I've defined my circuit, how do I actually target a device or a simulator to perform this circuit on? So let's say we want to use a Quantinuum device or emulator. We'll be providing emulator access for the hackathon, so you guys can play around with that. So we import this Quantinuum backend from the Quantinuum extension, this separate Python package. We can then specify that we want to emulate the H1 device. And then we can see which gates are supported natively by our device using this backend info option here. And then we see that we have this ZZ max gate, RZ, and several other ones there, which I'll talk about later if you like. Okay, so how do we actually compile our phase estimation circuit down to a form that you can actually simulate? This backend, Quantinuum backend has this get compiled circuit method on the class, and you can just pass in your circuit as a parameter, and Ticket will just solve for the constraints of the device or simulator automatically. So it will take care of your connectivity and all the constraints on the gate set that your device has. It's worth noting that I've not tried to optimize this circuit yet. I've just merely solved for the constraints of the device. So you can see that this compilation process has really substantially increased the overall gate count in my circuit. I've gone from about 20 gates in total to 96. Yes? Yes, good question. So, so there are several constraints. So like I said before, quantum devices typically support only a subset of gates, and your algorithm may be defined in terms of other gates. So these gates here are the ones supported by our Quantinuum device or emulator, but you'll notice that our phase estimation algorithm was defined in terms of these controlled U1 operations and Hadamard gates. So we need to somehow transform from that gate set to the gate set here. So that's one constraint. But another example of a constraint is for device connectivity. So you'll notice that, go back. Yeah, yeah, exactly. So you'll notice that I have all possible pairings of qubits here. So I've got qubit 2 interacting with qubit 3, and yeah, every possible pair is connected. But for instance, my device may only support nearest neighbor interactions between the qubits. So that's another constraint that needs to be solved. Yes?
In the current state of the art, how many gates is many?
That's a good question. I think I would say like a depth of like a dozen gates is quite a lot. Maybe like an overall gate count of like a couple hundred is like a fairly big circuit, I would say. Seon, do you agree with it?
At this point, it really depends on the device as well. There's a lot of trade-offs you can make with devices, and qubit number and depth are important. We're certainly getting to the point where on certain systems you can run depth 100 or so, and then for certain applications. But yeah, that's off the order. That's the
Yeah. I think it varies as well between different device types. So trapped ions may have a different answer to superconducting qubits and so on. But yeah, thanks. So I was here. Yes, so yeah, the point I wanted to illustrate with this slide is that just naively compiling your circuit can really increase your gate count here. So I've doubled the number of 2-qubit gates, so that will introduce more sources of error into my computation. So now say we want to optimize our circuit, try and sort of reduce the sources of error. So Ticket has functionality for doing this automatically. You can call this default compilation pass on your Quantinuum backend. This will essentially apply a tailored sequence of optimizations to your circuit. So the sequence of optimizations will be tailor-made for this specific device or simulator that you are trying to work with. So here I've specified an optimization level 2. This is the maximum setting, so I've tried to just reduce the number of overall gates in our circuit. So we have now 48 gates in total, and importantly, we have 11 2-qubit ZZ max gates, which essentially cancels out the overhead that we incurred by compiling our circuit naively. We have now have the same amount of 2-qubit gates as we did originally. Okay. And yeah, it's fairly easy to just swap out backends if you want. So you can also just use an emulator or a device from the IBM. From IBM, just using the Qiskit extension and just specifying your device as follows. So you can swap out devices and you can just use the optimizations for that device or whatever you like. Swapping backends. Ticket was designed so that swapping backends like this is supposed to be easy. Okay. So yeah, let's talk more about connectivity constraints. So yeah, as I mentioned earlier, if I view which qubits are connected to which other qubits in my phase estimation algorithm, for this phase estimation circuit, I have all possible pairs of gates interacting with one another. So I have this complete connectivity graph. And if I look at how the qubits are actually laid out in my device, you'll see that the connectivity is far more sparse. Here I'm talking about the IBM Bell-M device here. So I've got 5 qubits, and they have a sparse connectivity graph, and only adjacent qubits can interact with one another. Okay. Yeah, and you can just do the same default compilation pass on the IBM backend, like I said. So in addition to just applying this default compilation pass, and sort of, the good thing about default compilation pass is you don't have to know any details of optimization. You just get a good result, and Ticket solves this automatically. But you can also try applying your own passes individually. So we also have this full peephole optimized pass, which we can apply to our circuit. And this just essentially traverses our circuit looking for any redundant gate operations that we can cancel out, performing like local rewrites to the circuit. So yeah, we'll see that this is now converted to a different gate set, this TK1CX gate set here. And you can also perform the manual step of, oh yes.
Could you please tell us an example of a simplification performed by ticket gates that substitutes redundant gates that isn't something that humans can also trivially see? So, for example, 2 consecutive nodes.
Okay. Yes. So one example that springs to mind is merging adjacent rotation gates. So you might have come across these RX, RY, and RZ gates, and these just essentially perform single qubit rotations on the.
And you substitute them by a rotation R, N, theta, and N is a log reversor.
Yes, you change the angle of rotation. So if you have a long chain of these gates, you can just squash them to at most 3 of these rotations.
The Euler decomposition.
Yeah, you use the sort of Euler angle method there. But yeah, there are lots of other examples as well.
Okay.
But that's a simple one. Yeah, does that answer your question? Yeah, Sam?
So no, I was just going to ask, what do you mean by performed by a human?
Something that a human wouldn't write in the code in the first place. That's what
Oh,
I
okay.
meant.
Right, right.
But in this case, rotations are a good example because even if the human knows about the Euler theorem of decomposing the rotations,
Yeah, so here I can just define a rebase. A rebase is just a transformation between gate sets. So say I want to transform from the gate set in the previous slides back to the IBM gate set, I can define this rebase here using this auto rebase pass and then just passing in the operations which the device supports. So this X, SX, RZ, and CX gate set. And then you can just see that if I apply this, it just automatically transforms the circuit to the desired gate set there. So yeah, so you can sort of take control of this optimization process and perform steps as you like. One final thing that I'm going to say is that you can apply these different transformations in your own like custom order as well. So say I wanted to perform this full people optimize followed by the IBM rebase. So I could just create a list of those different passes and then just build a sequence pass by just adding that list there. And then I can just apply this sequence of transformations to my circuit. And this will apply the full people optimize first, followed by an IBM rebase. So you can sort of play around and try out these passes in different order. But if you don't want to do this, there's also the default compilation pass, which will just solve for your device constraints. One thing I don't have slides on, which TKIT also supports, is the ability to define a custom pass. So like a totally a pass that's entirely defined by the user. So there's some hackathon suggestions on that if you're interested. Yeah, so there's plenty of TKIT features I've not mentioned, which I'm happy to take questions on. We have application-specific optimizations for chemistry circuits. We have assertions for debugging quantum programs. We have extensive integration with Qiskit, which I've not really spoken about. And yeah, there's tons of other features which I've not touched on in my presentation. Yeah, so here are a bunch of useful links. I should say I'll be sharing my slides so you guys can all go through and click on these. And yeah, I've included these research papers from Quantinuum, as well as some documentation links to our user manual and our GitHub and so on. Everything's open source, so you can go and visit there and try things out. And yeah, that's just about it. So yeah, that's me. Feel free to ask any questions to Seon or I during the week. Also, just a reminder to join our Slack channel. The link is on WhatsApp. And yeah, the way you install. There's more detailed installation instructions, but you can just use these to install TKIT and the extensions. So yeah, thank you very much.
The ticket, what it does, is not actually, it optimizes
Yep.
your circuit.
Yeah.
And you can, instead of it optimizes automatically, you can instruct which part of
Yeah, so you, yeah, like exactly. So you can just use this pre-built optimization, which will work for whatever device you want to work with, or you can sort of, if you have an idea of an optimization which might work well for whatever application you're looking at, then you can build that in TKIT as well. Yeah, exactly. Any further questions? Oh, well, yeah. Thanks again.
which was Honeywell's quantum branch, who were building ion-trap quantum computers, merging with the company that Callum and I used to work for, / still work for, called Cambridge Quantum. And Cambridge Quantum was a UK-based company, and we were more software-focused. So we did things like build Ticket, build the chemistry package, work on quantum machine learning, quantum cryptography, this kind of stuff. So it's a merger of software and hardware companies, and now we do everything, is the idea. If you're interested in the company, there is a talk by Mark Jackson later in the week in the schedule in more detail. And there's an industry session this evening where we will be at a table where you can come talk to us. And if you do the hackathon, I have asked some people in the company nicely if we can have time on the Quantinuum emulator. So I think I have everyone's emails here. I'll make you all accounts, and then you can use the emulator if you so wish for a system that emulates the real ion trap device. Okay, so my plan is to go through this notebook, which shows you how to write the quantum approximate optimization algorithm using Ticket as a means of highlighting some in-depth Ticket features. Before we get into that, final chance to ask any questions on the stuff that Callum presented, if there is anything you didn't understand or wasn't obvious. Okay, I'm going to assume, yes.
It's not a question, it's more like a reassurance. Generally, if we don't have much experience in coding, because we don't have such a background,
Yeah.
do we basically, we use your slides as documentation and to see what we have to do?
Yes. So let me show you. This is the repository where all the stuff is on GitHub. It's fairly simple URL, github.com/cqcl/Qalypso_2022. And if you go there, all the material we're going to be using for this week is on there. And on the README, there is some content on how to run the notebooks. And there's a number of options as to how you run them. If you do want to code along with me today, you can just follow along the notebook and run everything that I run and edit it and play with it. There's a number of exercises in there that you may be able to do as well. If you want to do that, you can go to this repository, and probably for the purposes of this session, all you need to do is hit this button, and the notebook will launch in your browser.
Is there a way to get that link?
Can you put it on? Well, I mean, it should be. Let me.
Share it. We can paste it in Slack.
Yeah, I can definitely paste it in Slack. Or Callum can. Yeah. Or I can put it in big letters here. GitHub.com. Oh no, too big.
Yeah, it's in the Slack handout.
Oh, where's it gone? There it is. 4 letters /Qalypso, you know that one. And then it's the year that it is currently is. Right. Oh, too far. Okay, so on there, hopefully you make it there. If you hit this button, basically we've set up an environment where the notebook will run. And you'll get something that looks like this, pretty much identical to my screen. And in there, if you go into, so you'll land here. It won't let me anymore. But if you go into the notebooks folder, all the notebooks are here, and I'm going through QAOA notebook. Yes?
There's a Docker file in the repository. What does that mean?
Right. So this is, that Docker file in the repository is to tell Binder what to run. That's the environment. But if you want to run it locally, you can follow instruction 2 here, where I've put up the base image that it's using on a public registry, and if you just run this command, it'll pull it and run it, and you can it runs a Jupyter kernel there. Or if you're feeling confident and aren't scared of Python environments as you should be, you can do option 3 and install everything yourself. And the dependencies that you need are in base image and then packages.txt. There's just a list of dependencies for Python. This is more set up for the joint session later, which is meant to be more hands-on and interactive. So if you don't want to do this now, don't worry about it. I will go through this in more detail during that. OK. This one, I'm personally running the Docker image and running off that. OK. We may not get to the end of this. I'll go slowly. We will hopefully spend lots of time talking rather than just listening to me talk about code that may not make any sense. We will start with what QAOA is. I'm going to keep doing surveys. Who's heard of QAOA before? OK, I'm ignoring back row. Okay, so QAOA is an algorithm that was proposed not that long ago, I think 2015, something like that, for solving approximate optimization problems. Optimization problems are probably familiar to all of you. You have some function that you want to find the minimum of. That your function might be how long it takes a car to make it through a factory, and you have some variables you can control, and you solve that optimization problem. Approximate optimization is what it sounds like. You just want to solve it, but you don't necessarily want the exact optimal solution. You just want to be somewhere in the vicinity, so it's approximate. And QAOA, yes?
In the sense that you want to go to a local minimum, but you don't care if it's the absolute minimum, or in the sense that you can go near the absolute minimum, but not exactly there, but in a neighborhood of it.
It's more the latter, yeah. It's unlikely that you'd be happy with the local minimum. You are searching the approximate vicinity of the global minimum. Yeah. OK, so this algorithm was proposed as a way of using near-term quantum devices to solve this optimization problem using parameterized quantum circuits. As with other variational algorithms like this one that you may have come across, like VQE, I don't know if you covered them earlier in the day, there's no strict proven speedup. It's all heuristic and sort of approximation-based argument that it works. It may or may not be better in certain situations. We are going to look at using this algorithm. So I'm not going to go through the algorithm in much detail. It's the paper link is here if you want to go through it. I'll briefly introduce it, but it's a way of setting the scene for us to look at how to do this kind of stuff in general. So if you have an algorithm for solving optimization problems, you need an optimization problem to solve. The canonical one for QAOA is the max cut problem, which you may have come across before, but you can use it for any QBO type problem. Yes. So the max cut problem is you have some graph, i.e. nodes connected by edges, and you want to find a coloring of the nodes, i.e. assign one of two colors to each node, such that the number of edges between one color, say your color is red and blue, the number of edges between red and blue nodes is maximized. So a cut is all the edges that go between colors, and you want to maximize the number of edges that go between colors. So let's draw an example. We're using the NetworkX library here to define a simple graph. These are the edges of that graph, and then we draw it. And this, we've already assigned some colorings here. We've got 3 nodes, 3 edges, 2 colors, and in this case, the number of edges that go between colors is 2, these 2. I hope you can see my mouse. We good so far? This has applications in things, they're not particularly important, but it is a relevant problem. Okay, so we're going to try and solve this for general graphs using QAOA. Let's introduce the algorithm. So the idea is that we're going to use the quantum computer to prepare a state over the qubits that encodes a solution to the max cut problem. So if we think of our two colors instead of being red and blue as 0 and 1, and we number each of our nodes, so let's say this is 0, 1, and 2 as our nodes, and red is 0 and blue is 1, we can assign bit values to each node. So this is 0, 0, 1. And so that particular string of bits encodes a particular color assignment, and there will be a string of bits or a set of strings of bits that encode the max cut coloring or one of the max cut colorings. And that's what we're going to try and find. And specifically, we're going to try and prepare a quantum state where the qubits have those 0 and 1 states. And so by measuring those qubits out, we've solved the problem. And the way we're going to do this is by starting with the all 0 state of qubits and then doing a series of parameterized rotations on the qubits to get to another state. So this is our initial 0 state, and then each of these U's are unitary operations that are transforming the qubits one after the other. And these things in the parentheses are the parameters. So we talked about rotation gates earlier. In the simple case, this gamma could be some number, 0.3, and this U could correspond to a rotation about the x-axis of the Bloch sphere, an Rx gate. So these are sort of strengths by which to apply the operation. And what we're going to do is optimize these values until we reach a state that is good. Yeah, so I'll say a bit more about that later. Yeah, it'll get clearer, hopefully. So, yeah, so the idea is these numbers here, the gammas and the betas, are the parameters we can use to change the state we prepare in the end, right? By changing gamma and beta, we end up with a different state. And those are things we can control because those are inputs in our circuit, values in our circuit. And if there are p layers in our algorithm, it's a number from the algorithm, then you have per layer a gamma and a beta. So you get 2p parameters.
So psi is a multi-qubit state.
It is, exactly, yeah.
And you're doing the unitary matrix
Yes,
on it, but multiple times.
yes. Each with a different parameter. So this is gamma.
Each one, okay, has a different rotation.
Yes, exactly.
Why are there two types of parameters and
Yes, good question.
so the operators?
Yeah. So the inspiration for this algorithm comes from quantum annealing, where the general idea is you start with a ground state of a system that is easy to prepare, a Hamiltonian that is easy to prepare, and then you slowly evolve the Hamiltonian that you're applying to the system towards a Hamiltonian that you care about, so the problem Hamiltonian. And the idea of annealing is that if you do it slowly enough, then the state will remain in the ground state of whatever Hamiltonian you're currently at. So by the time you're done evolving, you'll be at the ground state of the target Hamiltonian. And what we're doing here is essentially encoding the optimization problem we care about as the Hamiltonian, the target Hamiltonian. So and the ground state of that Hamiltonian is therefore the optimal solution state. Sorry, did you have a question?
No, it was a physical question, but I don't think it's relevant to our discussion. I wanted to ask if in annealing there can be some problems with crossing of states when a ground state and a excited state, their energy, when you choose the Hamiltonian, changes and then they cross, and so this one becomes the new ground and this one becomes the new excited. But I don't think it's relevant to our purposes.
Yeah, I mean, I do think that's a problem, but yeah, probably for another time. Okay.
However, another question,
Yeah.
just to have some reading in mind. HB and HP,
Mhm.
what do the B and P stand for?
Yeah. So I can't remember. Do you remember what B stands for? P stands for problem, I think.
So B, I know that it's the cost and mixer layer. So B is the mixer layer. I don't know why it's called B, but B is just some X rotations. And cost layer is the layer that encodes the connectivity of your graph. So your cost Hamiltonian you construct directly if we're looking at a graph. And the mixer layer is always just X rotations.
In general, the cost Hamiltonian is the Hamiltonian that encodes the problem you're trying to solve, the optimization. That encodes the energy landscape of the optimization you're trying to solve, such that the ground state of that Hamiltonian is the solution. So this kind of expression here, if you've seen the Schrodinger equation before, it's evolution under a Hamiltonian, right? I've got a Hamiltonian here, and I do.
Yes, I just wanted to ask what do the letter B and the letter P stand for in the subscripts?
I think it's some particular thing from the paper.
So
Yeah.
P stands for problem.
Yeah.
I can't remember what P stands for.
Okay. This is evolution under the target Hamiltonian that you care about, and this is something that's kind of thrown in as a heuristic to QAOA. It's the mixer. It is essential, but the mixer essentially evolves the system under a kind of orthogonal Hamiltonian, such that you get mixing of states that are not just from the subspace that you started in. I don't want to get into too much detail on this, but you essentially evolve under the problem Hamiltonian you care about, and then you mix things up a bit and evolve some more, and mix things up a bit and evolve some more, in the hopes that it's the kind of exploration exploitation trade-off kind of idea. Right. So we have a degree of freedom here. We can decide how many layers we do this for. We can do one. We can just evolve once, or we can do more. And the more you do, the more slowly you're evolving the system, and the more accurate you expect your results to be. But the more you do, the deeper your circuit gets, and therefore more noisy. So let's think about defining our cost Hamiltonian for the max cut problem. The cost function is very simple. If at node I have labeling x or color x, then I can define a cost function as this sum of xi. So if I have two nodes, I and j, I can define the cost function as this sum of xi times 1 minus xj. So for example, if my two colors are red, 0, 0, then this goes to 0, and so on. So every time you have mismatched edges, you get a one term, and it adds up. So this counts the number of edges we care about.
So in other words, it just counts the number of edges.
Counts the number of edges between mismatched colors.
Okay.
Yeah. Now, here is some stuff you might have to take on faith a little bit. We could go into more detail, but once we've encoded our problem in these 0 and 1s on the qubits, we can write this. We can write a Hamiltonian, this Hamiltonian in particular, that if we measure, we get this cost function out of. So specifically, that happens because we essentially put a Z measurement on per term. So this is a number of terms that we can expand, and in our case, that there's a term per edge, so that'll be 3 terms, and it amounts to, for each edge, measure the qubit that edge corresponds to, and find this term from them. So by doing this tensor product. Yeah, we won't spend too long on that. And then the mix of Hamiltonian has an even simpler form, which is just apply an x to each qubit. Okay. So this is just the same thing, but said in more general. So we can this xi variable we can map that to the quantum case by doing this transformation. And then you can use that mapping to write the problem Hamiltonian in this way and the mixer Hamiltonian in this way. But remember, once we have these to do the actual state evolution, we need to do this exponentiation by the parameters. All right, let's just ignore some warnings and delete that. Yeah.
If I understand correctly, the cost function is something that you calculate in the end to see how many good connections there are.
Yeah, so it serves two roles. One is you do a measurement at the end to find out how good the state you've prepared is.
You can use it as a measure to, you want to maximize this.
Right, exactly. But it's also the thing you evolve under, right? So it's also in here. So it's also used to actually prepare the state during the circuit. Okay. And we'll look into that now. So circuit construction for QAOA. We're going to define the graph we're interested in here using these edges. We set the number of nodes it has, and then we'll just draw it to visualize it. Looks like this. And hopefully you can see some numbers on the nodes. These are the numbers of the nodes that we're going to keep referring to. So it's 0, 1, 2, 3, 4, 5, 6. And here we've written down the correct max cut colorings we expect for this. Now, hopefully for this simple example, you should be able to just read, see what the right answers are. I mean, the simple way to proceed is just start assigning colors and see how far you get, right? So I could assign a 0 here, and then I want this edge to be between different colors, so I could put a 1 there, and then another 0 here, and then 0 here, 1, 0, 0. And then we would have maximized, all the edges would be between different colors. Or, of course, I could just take the same thing and flip the 0s and 1s, and I'd get an equivalent result. And that's basically what we've encoded here. Hopefully that makes sense. Yeah, so if the order of the numbers here is if there's a 0 at a certain position, it means assign color 0 to that node. So this 0 there means assign color 0 here. So if I map my naive solution of put one color here, another color here, the first color here, the second color here, and the first color here, then I get these two solutions. All right, and we'll use these expected results to evaluate the performance of our algorithm later. Okay, so throughout the notebook, there are these red exercise boxes. If you're sufficiently bored and you think you know all this stuff, try doing them. Otherwise, there will be time during the joint session later to try these and ask questions as you do them. As in, we'll be wandering around and can help. Okay. Right, so now we're going to define the cost Hamiltonian. Here we start using some PyTicket tools. So as well as doing circuit construction and optimization, we have some operator-defined utilities that can help with this. So this is the qubit Pauli operator. That is essentially, you can think of it as, let's see. You can think of it as a thing that can represent all of this in one go. I have a set of Pauli operators on certain qubits, and I have some coefficients in front of those, and representing the sum of those terms. And each of those terms is represented by a qubit Pauli string, so just a string of Pauli operators. And each of those is made up of Paulis. And we're going to use our representation of qubits as well. So this function that we've defined here can take your list of edges for a max cut problem, and this gamma term here that we're going to put in front of it as our multiplier, and it will build the correct operator for that Hamiltonian for you in terms of the qubit state. And how it does that is first we just make the identity term here. So that's no Paulis just means identity on everything. And then we put in our cost angle. So that ends up as this term here. And then for each of our edges, we say we want to do a ZZ operator to measure the x times 1 minus x function on the 2 qubits corresponding to that edge. And then we just say, and multiply that by minus 0.5 times our multiplication angle. And we can put all of that into a qubit Pauli operator and use this for our particular case and print it, and we get a nice LaTeX representation of our operator. Actually, no, that's not true. We get a Python printout. The LaTeX representation was there previously. But as a Python object, this is what it looks like. Okay. So that is just the cost Hamiltonian. We're now going to use that to build a circuit that does the evolution under that Hamiltonian. We have a handy utility for that too. Gen-term sequence circuit can take a Hamiltonian with a coefficient like the gamma we have, and then prepare a circuit